Last time we learned about the basics of confidence intervals and basically how they're constructed, right? So you start with a point estimate, which is a statistic, something you calculate from a sample, and that's your best guess of the population parameter. But as we know, if we took a different sample, we would likely get a different point estimate just due to sampling variability. So we figured out, okay, well, we can use the fact that we know the sampling distribution will be normal if certain conditions are satisfied, and we know how much data is contained within certain standard deviations in a normal distribution, right? 68% within one, 95% within two, 99.7% within three. So we can construct a margin of error surrounding that point estimate to kind of account for some of that sampling distribution. And that'll give us an interval of plausible values that we think will likely contain, with a certain percent confidence, the true parameter that we're looking for, right? The true population value that we're trying to figure out. So today we're going to specifically focus in on proportions as our statistic, right? So you can think of this just like polling, right? Polling for an election, you see a bunch of confidence intervals for proportions. All right. And so we're going to focus in on the conditions we need to check, and then I'm going to teach you how to use your calculator to actually calculate these sampling distributions. And again, we'll interpret them like we did in 8.1. All right. And so these are just our targets. We want to be able to state and check the random 10% large count condition. This is something you'll have to do for pretty much every statistical inference procedure we use for the rest of the year. So this is kind of the first day we're going to do it, but this will become second nature and probably very cumbersome and annoying because it's just like, it's a box you have to check. We'll talk about determining the critical value for a certain percent confidence interval. So the critical value is basically how many standard deviations do you want to go, and then to either side. And then we'll talk about how to construct and interpret a confidence interval, and finally how to determine the correct sample size you need to take to get a certain percent confidence interval. That last one is really important in real life because, as we know, sampling costs money and takes time to get an appropriate sample, because we can't just, especially for polling, you can't just sample in downtown Phoenix. So that's not going to be representative of the rest of the people in Arizona, right? Probably not similar opinions to those people who live in Yuma or whatever. All right. So here we go. When proportions are met, a C% confidence interval for the unknown proportion P is this. This is straight up the formula for how you find a confidence interval for a proportion P. And as you do this, I printed out each of you a packet of your formulas and tables. So I want you to open this up, and you can see this formula will be in there. Oh, shoot. I'm one short. Oh, no, like that. I'll just staple this one for you. So this formula is not explicitly stated, but it is stated in kind of pieces. So on the second page, you have your confidence interval verbal statement. And then on the third page, at the top, you have your formula for standard error of a sample statistic. So you can kind of piece together how to find the confidence interval from that. All right. So remember what a z-score is. It's just a number of standard deviations from the mean. So this portion here, this is just our margin of error. p hat is just our point estimate. And then to break, your margin of error really consists of two things. And that's a z-score, which we call a critical value. That's just the number of standard deviations, because that's exactly what a z-score is. It's a how many standard deviations from the mean, right? And so that critical value is really what determines your confidence level. Again, if we want 95% confidence, how many standard deviations from the mean contain 95% of the data? 2. So your critical value would be about 2. Now, that 2 is a rule of thumb. It's actually like 1.96. We'll talk about how to use your calculator to actually find the more accurate version. Because sometimes we may want to create like a 93% confidence interval or a 97% confidence interval. And so we can use our calculator to figure out what the appropriate critical value is for those as well. All right. And then this is just your standard deviation of your statistic. Now, it's actually not. I lied. Not fully, but before, the standard deviation formula didn't have p hats in here. It was just p, right? It was square root of p times 1 minus p over n. But the problem is p is the parameter that we're looking for. So do we know p? No. So it doesn't make sense that we would be able to use p to find that standard deviation. The best estimate we have for p is p hat, right? Okay, so this really isn't the standard deviation because we're not using p. So instead we give it a new name just to delineate between standard deviation when we're using the true parameter and when we're using an estimate of the parameter. We call this the standard error of the statistic. And you'll see that in your formula packet. If you flip to page 3, it's actually labeled as standard error. And all that means, again, is that we're not using the true parameter. We're using our best guess of the parameter to compute the standard deviation. It's at the top of page 3, I think. All right. Does everybody feel okay about that? Okay. All right, so 3 conditions must be met for that formula to be valid, okay? The first condition is that it has to be a random sample. This is pretty much the most important. You have to check these conditions, and you, not in your head, you have to state them. Which again, gets a little cumbersome, especially after doing it 9 years in a row. But you guys luckily only have to do it 1 year unless you go into statistics, then you'll just constantly be doing it. But you have to state, for the AP grader, you have to state the sample was stated as random. This will generally just be stated in the context of the problem. And there's not going to be these gotcha questions, guys. It's not going to be like, construct a confidence interval, and you go through this whole 10-minute process of writing all this stuff out. And then they're like, just kidding, what they didn't say was a random sample. You got the whole thing wrong. It won't be that. No, there may be a question where they're like, specifically, are all 3 conditions satisfied? And that's likely to be a multiple choice question where it's like, yes, or no, the random one isn't necessarily, or no, the 10%, or no, the large counts. But it won't ever be a free response problem where they try and trick you into doing a really long process when one of the conditions isn't satisfied. All right, so it has to be a random sample. Large counts. Remember that for the sampling distribution to be considered normal, this has to be satisfied. Now, normally it was n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. But again, we don't know p. That's what we're trying to figure out. So our best guess of p is p hat. So that's what we use for large counts. And that just tells us we can use a normal distribution, because we know that sampling distribution would be approximately normal. And then the last one, and don't feel like you need to write down all these words in the prompt. What I circled in green is the important part. It's the large counts. This is sometimes called the check for normality, because it just tells us that the sampling distribution will be approximately normal. The last one is a check for independence. We call that the 10% condition. And that's just that your sample size is less than 1/10 of the population. The way I usually check this, it's a little easier, is just multiply your sample size by 10 and make a statement that it's safe to assume that that's less than the population size. And that just lets us know that it's okay to assume that the individuals in our population are independent of one another. So it's always going to be these three conditions. So we call them random, large counts, and 10%. All right. And this is something I already said, right? When the standard deviation of a statistic is estimated, we call it the standard error instead of the standard deviation, right? Because standard deviation uses the true population parameter that we don't actually know. All right, so just to review, the way we construct a confidence interval is you start with a point estimate, you add and subtract the margin of error. And an equivalent form, this is what's actually in your formula packet, is you start with a statistic, and your margin of error actually consists of these two things. Your critical value, which is how many standard deviations do you want to go, and you multiply that by the standard error of your statistic. And again, that's in this actual phrasing is in your formula packet. All right, that's just a summary about the three conditions we need to check: random, 10%, large counts. Let's do an example. All right, Mr. Buckley's class wants to construct a confidence interval for P, the true proportion of red beads in the container, which includes at least 3,000 beads. Recall that the class's sample of 251 beads had 107 red beads and 144 other beads. Check the conditions are met for constructing a confidence interval for P. All right, so here's how you're going to check the conditions on paper. I just do them like this, kind of bullet point style. Random. It doesn't say in here that it's random. It just says it's a sample, but when it does that, just go safe to assume that it's a simple random sample. We'll assume that they just shook up a jar of beads and then took a handful out or whatever. All right, 10%. For that one, I like to take my sample size and multiply it by 10. So it's a sample of 251 beads. So 251 times 10 is 2,510, which is less than the population size of 3,000. And that's all we need. So that's checked. Right, the population size is stated as 3,000 beads. Now, for large counts, I need to know my p hat value. Let's break out the calculator. We're looking for the proportion of red beads. We had 107 red beads out of 251 beads. So what's our p hat value? So what's 107 divided by 251? About 0.543, is that what you said?
0.426.
Oh, 0.426. Great. So that's our p hat value. So that's what we're going to use to check large counts. And remember that large counts is n times p hat has to be greater than 10. So my sample size, which is 251, times p hat, which is 107 divided by 251. Well, that's just going to be 107, right? That's definitely greater than 10. And then you need to do it again. 251 sample size times 1 minus p hat. So what's 251 minus 107? All right, so that's 144 out of 251. And that's going to be 144, which is also greater than 10. Great, so our large count condition is also met. And we're done. So this is always going to be your first step to constructing a confidence interval, is to check the 3 conditions. So generally on like an exam, if I give you a prompt and I ask you to construct a confidence interval for a situation like this, that could be like an 18-point problem, and this is 6 of them. So like 2 points per condition. One that you stated the condition, one that you correctly checked the condition. Okay? All right. So there you go. This just goes through it. All right, so how do we get the critical value z star for our confidence interval? So for a 95% confidence interval, what we want is in the standard normal distribution. So we haven't said that in a while, but that's the one that has a mean of 0 and a standard deviation of 1. And that means z-scores are the values on the x-axis. So what you want to do is figure out the z-scores that bound whatever percent of the area that you want your confidence level to be. So if we want it to be 95%, we're trying to figure out the z-scores, namely positive z-star and negative z-star, that bound 95% of the area. Now we know from the rule of thumb that should be approximately 2, right? But again, I said that's a rule of thumb. So we can figure this out exactly, actually. We have a function in our calculator that allows you to input an area, and it will give you an output of a z-score. And that function is inverse norm. And the input you give it is the area to the left of the z-score you're looking for. And then you want your mean to be 0 and your standard deviation to be 1, okay? But this will take a little bit of extra effort unless you have one of the newer calculators with the newer operating systems. Then it lets you choose what area you're inputting. But I would just keep it the standard area to the left so that we're all doing the same thing and learning it the same way. Oh, is it? Oh, well, I guess it's been sitting there for a year. So.
Well, yeah.
Okay. So when I say that, if I want a 95%, oh my God.
I'm sorry.
No, it's not your fault. I didn't even think about it, that they just sat dormant and probably the air conditioning was off. So is this one. Here, just use mine because I'm going to be using the computer one.
Sure?
Yeah.
Okay, thank you.
All right. So here's what I was saying. It doesn't matter which of these z-scores you find. But if you find this one on the left, it's going to return a negative z-score. That doesn't matter because remember, we're doing plus or minus. So if I go, sorry, I'm going to go way back here. This is plus or minus the critical value times the standard deviation. And they're symmetric. So they're going to be the exact same, just one's positive, one's negative. So let me show you what I mean. In our calculator, if we're looking for that 95% critical value, I would input inverse norm and let's say I want to find the one on the left. Well, the area to the left of that is 0.025, right? So I would put 0.025, comma 0, comma 1. Which one? Oh, no, I haven't done it yet. Sorry, I was just writing this out. I'm going to pull it up now. All right, so then that's in the distribution menu. So I'm going to go second vars. We got inverse norm. See, this is one of the newer operating systems, so it lets me choose what area I'm inputting, but just keep it left. If you have like one of these, it defaults to just area to the left. So I'm going to put my area as 0.025. And again, if you have an older operating system, it won't give you this menu. You'll just input it like this without that left. It'll just be 0.025, comma 0, comma 1. And I get about 1.96, negative 1.96 in this case, right?
In your calculator, it takes you to the y equals menu and it takes you to the
Huh? Here, just quit out of that. Just go a second. All right. There you go. It was just probably already in the y equals menu. All right. And like I said, you could find either critical value. The other one, the positive one, is just going to be the exact same, but positive. But what area would I enter if I'm looking for that critical value up there? What's the total area to the left? Meaning this and this. What's the total area to the left of this critical value? So you have the 0.95 plus the 0.025. And that's just 0.975. Does that make sense? And then if I hit enter, just note you get the exact same critical value, it's just positive. So it doesn't matter which one you look up one of them, because you're going to do plus or minus the critical value times the standard error anyway. Does that make sense? Okay. So that's how you find the appropriate critical value. I'm not even going to talk about how to use the table because it's ridiculous. All right, let's do this. Let's construct a confidence interval. So we're going to kind of walk through a full example here. All right, so according to a 2016 Pew Research Center report, 73% of American adults have read a book in the previous 12 months. Definitely part of the 27%. This estimate was based on a random sample of 1,520 American adults. Assume the conditions for inference are met. This is the only case in which you don't have to check those three conditions. They're letting us assume that they're met in this case. So good, we're done with that. random, large counts, and 10% are met. Let's determine the critical value Z star for a 90% confidence interval for a proportion. So to help us do that, I always just like to sketch out what's going on. So we know that we're dealing with a normal sampling distribution, so it's going to be like this. I'll put my mean of 0. I'm looking for the Z star or the negative Z star, whichever you wish to find. They're going to be symmetric. That contains what percent of the area? So 0.9, right? Great. That means what's left in the tails? How much total is left in the tails? 10%. So how much is left in each tail? 0.05. So this is 0.05 and this is 0.05. All right. So if we want to figure out our critical value, and generally when they specifically ask you for the critical value, we just list the positive one. Even though there's a positive and a negative one, it's just convention that we'll list the positive one. All right. All right, so one way I could do this, I could either do inverse norm and input the area as 0.05, and that'll give me this one. Or I could do inverse norm and input the area as what for this one? How much area is to the left of that one? 0.95, right? Either one. So I'll do the 0.95. And that'll give me the positive one. Enter. We'll just go to 2 decimal points. So about 1.64, right? Or 1.645. We should actually probably go to 3. Sorry. 1.645. That makes sense because we knew that 95% was about 2 standard deviations. So 90% should be less than that, right? Great. All right, B, construct a 90% confidence interval for the proportion of all American adults who have read this book in the previous 12 months or read a book. All right, so B. All right, first thing I need is a value for P hat. And they don't. Oh, it's 0.73. They do just straight up give it to us. Good. So 0.73, right? All right, so now I'm going to use my formula for a confidence interval. You start with your statistic, 0.73. You add and subtract a margin of error, which consists of a critical value, which for us is 1.645, times the standard error of our statistic. And that's that formula that's in your formula packet. Just real quick, go back and remind us what it looks like. Even though it's super far back, it's this one right here. Root P hat times 1 minus P hat over M. Did I go too far? There we go. All right, so times the square root of P hat, which is 0.73, times the complement of that, which is where I fall in this little experiment, the 27%, 0.27. And then we divide by the sample size, which is what, 1520? Great. And we actually want to create an interval out of that. So we don't just want to leave it like this. We're going to create an interval. So we're going to do the 0.73 minus 1.645 first. I'll show you a little calculator trick. Which I've been using here. But if I type in 0.73 and I do the minus 1.645 times the square root of 0.73 times 0.27 divided by 1520. All right, this should give me the lower endpoint of my confidence interval, right? Enter. Just going to write that down, 0.711. All right, so to find the upper, here's the trick. I don't know if you guys already know this, but you can hit second enter, and it'll pull up your last input and just let you edit it. So then I can just scroll back and change my minus to a plus. Enter, and then there's my upper endpoint. So 0.749. Okay. So our confidence interval is 0.711 to 0.749. And now we interpret. And so this is the script from last time. We started out with the royal we. We are, in this case, 90% confident that the interval from, I'm gonna write these as percentages just because they gave us the statistic as a percent. So 71.1% to 74.9% contains the true percent of American adults who have read a book. In the past year. So that's like 75% of a problem where I ask you to create a confidence interval, is just that. The 25% we're missing is we just didn't go through and check conditions by hand like we did on the previous one. All right. Now, here's the good news. You don't have to do this really again in terms of calculating the interval by hand. This part is unnecessary to do by hand. Your calculator can do that for you. So let me show you real quick how that works in your calculator. So let's go to calculator. We're going to go to stat, calc. Oh no, that's not where it is. Go to stat tests. Whew. So stat and then all the way over to tests. And we haven't gotten into tests. Right now we're talking about intervals, right? And a thing to note, like with the syntax of your calculator, anything that says prop is for a proportion. Anything that doesn't say prop is for a mean. Like I said, there are two statistics we're going to focus in on, and it's proportions and means. So anything that has prop in the title is for a proportion. Anything that doesn't have prop in the title is for a mean. So what we're looking for is a one prop z interval, meaning we took one sample, it's for a proportion, and we call it a z interval because we're using these z critical values, okay? So it's called a one prop Z interval. And so I'm just going to scroll down until I find that. That's one prop Z test. That's not what we're using. There we go. So it's at choice A, a one prop Z interval. And I'm just going to hit enter. All right. So remember that to create a p hat value, the way we create p hat is we do x over n, meaning number of successes over sample size. So p hat equals x over n. Now in a case like this, they didn't give us the x. They just straight up gave us the p hat value, which is 0.73, right? But they did give us the sample size, correct? So we can figure out x by just multiplying p hat by the sample size. So if I do 0.73 times 1510, that should give me the number of successes. So in your calculator, they specifically want that. So 0.73 times 1510 for x. It's 1520. I'm sorry. Thank you. So times 1520. And here's another weird thing is that I don't think x, they won't allow a decimal. So whatever it is, just round it to the nearest whole number because it'll give me an error if I let it be 1109.6. So I'm just going to have it be 1110. And then n is 1520, right? And so you should always have it so that if you divide those first two, that should give you your p hat value. All right, confidence level is just your confidence level. We wanted it to be 0.9, right? And then calculate, that's pretty self-explanatory. There we go. That gives us the exact same confidence interval that we just calculated. Gives us the p hat, etc. So you're 100% allowed to just use your calculator, but just like before, you need to tell me what the label was. This is a one prop Z interval, or a one sample Z interval for proportions if you want to be wordy about it. And then you just need to tell me what the inputs were. So what's x, what's n, and what confidence level. Does that make sense? Okay. So the text we use likes to organize statistical problems as a four-step process, which is state, plan, do, conclude. And you don't have to write out state, plan, do, conclude, but it does help you make sure you don't forget things that could lose your points. So state is like state the parameter you want to estimate and the confidence level. Plan, check conditions, basically. Do, perform calculations. So this is where you tell me what you're using a one prop Z interval, and you show me the calculations. And then conclude, make sure you interpret your confidence interval. And again, this isn't something that like the AP, the College Board specifically looks for. This just is a kind of an organizational method that'll help you make sure you don't leave anything out that you do need to earn full credit. All right. So let's put this all together and do just a full-on confidence interval problem. All right, so a recent poll of 738 randomly selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on their cell phone. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. All right. So if we use the four-step process to organize our thinking, the first thing we're going to do is state the parameter of interest. We're going to make a 95% confidence interval for P, and P is the true proportion of all cell phone users who walk into stuff. Would you guys admit that?
It hasn't been talking on the phone for me. It's been like looking, and I don't usually. I walk for sure.
I don't think I've done that, but I do take my phone running and constantly eat shit when I run. Super embarrassing ways.
I feel really hard to run into someone who's like making a call. Yeah, because if I'm talking on the phone, I can look for it.
Do you guys make calls?
No. Mostly because like my dad calls me.
Yeah, I don't know. If my wife calls me, I'll answer the phone, but that's about it.
For college, sometimes like I don't know.
Do you guys answer the phone if it's a number that's not somebody in your phone?
No, absolutely not. I like I can do. Only if I feel like I'm expecting something. It's like colleges was like, yeah, call you random.
Yeah, that's rough.
So random. So if it's like from a state and it says that it's not spam, then I pick it up. But now
Yeah,
I don't. But like,
right. That makes sense. All right, plan. Let's check our conditions. We're going to make a one sample Z interval for proportions. State that it's random. It's a random sample of 738 cell phone users. Done. 10%, the way they check it is they just say it's reasonable to assume that 738 is less than 10% of all cell phone users. Like I say, I just like to multiply the sample by 10. So I would say reasonable to assume the population of cell phone users is less than 7,380. Either way, that's fine. Again, we're checking boxes here. This isn't rocket science. We just have to do this. And then large counts is n times p hat and n times 1 minus p hat, which really comes out to the number of what we would consider successes. Successes being people who, I guess, walk into stuff. And then failures, which is the complement of that. So 170 and then 738 minus 170, which is 568, are both at least 10. That satisfies our large count condition. All right, so let's practice using our calculator for this. So let's do the do section together. So we're going to use our calculator to construct that one prop Z interval for P. Okay, and in this case, so it's a one prop Z int for P. And in this case, X is going to be what? What's the value of the number of successes? Number of successes being people who walk into stuff. So that's 170. N is going to be 738. Sea level, 0.95. And that's it. Now we're just going to pop that into the calculator, and that'll get us our confidence interval. And we'll fill it in right there. So we go to stat tests. It's option A, 1 prop z int. We'll just do 170. 738. 0.95. There we go. So it's I'm just going to call that 0.20. 0.26. I'm just going to write down what the actual p hat is. 0.231. All right. That's it. So now we have our confidence interval. So basically, somebody verbalize what the conclusion would be. How do you interpret that? Do we remember the script? Sam?
We are 95% confident that the interval from 0.20 to 0.26 contains the true proportion of people who walk into others while talking on the phone.
That's it. Perfect. There it is on the board if you need it. We're 95% confident that the interval from 0.20 to 0.26 captures the true proportion of all cell phone users who would admit to walking into something while talking on their cell phone. Well, this is would admit to, yeah. I've eaten it so many times while running. I did it once just on Central, like in front of a bunch of onlookers.
You just like trip over?
Yeah, I'll just be like running and kind of fatigued and not paying enough attention, and it'll be like a crack right here, just like straight onto my face. Phone goes flying. It's the skateboard is one of the worst because it's so frustrating when you hit like a pebble and it just stops your board dead. You just go.
Yeah, well, but they suck so much.
All right, here's what we're gonna do. I'm gonna stop there. There is a little extra section, which is how do we find what sample size produces the confidence level that we'd like. It's pretty short. We're going to do that next time, and then we'll do a formative assessment. And then, like I said, I'm going to start moving into non-book problem sets and more problem sets that look like the formative assessment starting on Monday. But this problem set is from the book that I posted for this section, but it'll be the last one we do that way. So you have a problem set for 8.2. You can get started on that, and we'll finish up our last few slides next time, which is how to choose the appropriate sample size.